Friends, welcome to our channel Google Galaxy. Today we are going to discuss. Today our topic is space isomerism. This is the part of coordination compound. Make sure that you have seen the previous series, part 1, part 2, which is part 1, part 2, part 3. Okay, when we talk about the space isomerism, this type of isomerism occurs in heteroleptic complex compounds. So condition for the space isomers that this type of isomers occurs in heteroleptic complex compounds. What are heteroleptic complex compounds? In which different types of ligands, more than one different types of ligands are present, which differ. These types of heteroleptic complex compounds which are present in space isomers are different from one another in spatial arrangement, in the space arrangement of ligands. What are ligands? Ligands may be atoms, may be group or ions around the central metal atom. Around the central metal atom, it arises due to the directional nature of coordination bond in which the ligands are attached to central atom. Okay, overall I mean to say that it is of two types. It is of two types. It may be geometrical, it may be optical. It may be geometrical. Its second type is optical. First we will discuss the geometrical isomers, then we will go for optical. When you say geometrical isomers, it is due to the ligands occupy the different positions around the central atom or ion. In geometrical isomers, we say that the ligands occupy different positions around central metal or ion. These things you need to remember while drawing any structure. The isomers in which the similar ligands occupy the adjacent positions are referred to as cis isomers. If I am having this example, now they are at adjacent positions. This type of isomers in which the similar ligands occupy the adjacent positions are referred to as cis isomers. Another metal, if I just say to complete this structure, if chlorine is present over here, adjacent metals, or I can say iron, occupy the adjacent space positions. We call it as cis isomer. If the isomers of similar ligands are at opposite positions, we refer to as trans. It means that the chlorine is shifted towards to this side and the NH3 is shifted towards the another side. We will call it as trans. So again, when we say adjacent side, we call it as cis. When cis is what? Cis is when adjacent sides, we call it as cis. What about the trans? When they are at opposite sides, we call it as trans. So overall, this type of isomerism is known as cis-trans isomerism. This type of space, or I can say stereoisomers, is very much important in the complex compound with coordination number 4 and 6. So point to be noted that when coordination number is 6, 4 or 6 geometrical isomers, out of this possible space arrangement, when we say the stereo space isomers, we will use the coordination number 4 and 6. Out of these two possible arrangement, geometrical isomers, when we say 4, it means they are having two structures. It may be square planar or a tetrahedral. When we say 4, coordination number 4, the two possible arrangements are possible. Two arrangements are possible in complexes. It may be square planar or it may be tetrahedral. Only square planar show the stereoisomerism because this is tetrahedral complexes. Next we are having the different types of square planar complexes. So again, why? Okay, the coordination number 4, that is it has two possibilities, scale planar and the tetrahedral. Only square planar complexes show stereoisomerism. This is because the tetrahedral complexes, all the positions are adjacent to each other, so that is why we use the square planar. So moving towards the next, we are having the different types showing the geometrical isomerism. The first type is we are having the square planar complexes. This is the type with the metal ion M and the ligands of type A2, B2. We call it as type. A common example of this complex showing the isomerism of common type PT is acting as M, as metal ion, where ligands is of this type. While naming this compound, we will need to read in the reverse order. We will decide the alphabetically order. We will call it as diamine dichloroplatinum with the oxidation number 2. This is the name of this complex. It exists in two forms. One is cis, another one is trans form. The cis form is pale yellow, while the trans is in dark yellow in color. This cis form is very much popular. What is its practical application? Why we are study stereoisomerism? Because this type of geometrical isomers helps for the treatment of diseases. So I am going to say that this type of cis form is an anti-cancer agent. This form of cis is used for the treatment of as a medicine. This cis form is also known as anti-cancer agent and has become very popular over the years, and has become very popular over the years. As I already draw the structure of cis form, if I just say how we can this is cis form, so it has pale yellow color. If I just draw the second isomer, we will need to move the NH3 to adjacent side, opposite. Now this form is transform. Another type we are having this square planar complex with tight metal along with the multiple ligands. In this case, the two ligands are attached to the metal atom. Are same, while the relative position while their relative positions in square planar complexes are responsible for different isomers. For example, I'll give the example. After that, it will clear to you. You will have to just learn the type. After learning this type, after you learn, you are able to draw any type. Now, for this type of square planar, first let me draw, then I will explain. Okay. The two ligands are attached to metal atom, are of same type, and their relative position in the square planar complexes are responsible for different isomers. Relative position, this one is cis form, this one is trans form. Their position is responsible, these are of same time, their position is responsible for the different isomers, as I told earlier. Sorry for inconvenience. Next we are having the third type. So I'll repeat again. In this case, the two ligands are attached to a metal of same type, are of same, and their relative position in a square planar are responsible for different isomers. Here its position, their relative position in a square planar are responsible for the different isomers. Next we are having the third. Next is our third type of geometrical isomer. Square planar complexes. We are having the M is the central metal, where AB is acting as the ligand. Here AB represents the unsymmetrical bidentate. What is AB representing over here? AB is unsymmetrical bidentate. Unsymmetrical bidentate ligand. If I'll give you the example of this third type, for example, we are having the platinum glycinato complex. Platinum glycinato complex. This one is our complex. What is the here GLY is what is the formula for GLY? The formula for GLY is NH2 CH2 CO minus. How we can draw this square planar? Take a look. We are having platinum over here. Around side we are having the ammonia and oxygen. So amine, NH2 is amine, and these two oxygen. So we will write it as NH2 This is our structure. Similarly, we are having to this side. This one is the, since I have written over subscript as a twice, so we will draw it twice. This one is example of another type of geometrical isomers. The fourth one, we are having the fourth type is the square planar complexes with MA BCD type. That means all the 4 atoms joined to central metal, or I can say all the ligands linked with the metal line are different. Such compounds are exist in 3 geometrical isomers. In writing their structures, their position of one of the ligand is kept fixed in a scalar planar complex. The remaining 3 ligands are placed in transposition one by one. If I'll give you the example, you will understand what I was saying. If I'm having this type of example, if this coordination compound is given to us, as I told earlier, that here 4 ligands linked with the metal line are different. These compounds exist in 3 geometrical isomers. So here we are going to draw the 3 geometrical isomers. One of the ligands is kept fixed in the scale planar. The remaining 3 ligands are placed at transposition. I'm going to draw 3 geometrical isomers. Similarly, we are having the another type. The third isomers we are having the okay. In these 3 geometrical isomers, we kept the NH3 constant. Amine at a fixed position is kept at fixed position in a scalar planar complex, while the other 3 ligands are at transposition. This is all about the scalar planar. Next we are having the another complexes, octahedral complexes, with the coordination number 6. It has its 2 types. The first type of octahedral complexes is we are going to discuss one by one. These are the 2 types of octahedral and geometrical isomers. Then after that we will going to discuss the optical isomers. Okay, for tetrahedral complexes we are having the only 2 types of geometrical isomerism. Some of the common examples I am going to list. The first type for the octahedral is first type is Ma4B2 type, and the second type is this one is the second type for octahedral complexes. In octahedral complexes it can exist in, that is the octahedral complexes. If I'll give the example of this type, this one is the example for the octahedral complexes. The octahedral complexes with this type can exist in cis and transform. It can exist in cis as well as transform. In this case, the cis is having the violet color and the trans is having the green color. How we can draw the octahedral structure? We will need to learn that method. For the octahedral complexes, here cobalt is acting as a metal line where different types of ligands are present. two chlorines are present, so we will draw all the ligands which are in the coordination sphere. We will draw both the cis as well as trans. Now this one is called cis form. Another one we are having the trans form. We also called it as trans isomer. Now this one is called transform. It is having the green color, it is having the violet color. What is happening over here, that the two elements are adjacent to each other, while these two are these are opposite, these are at opposite sides, these are at adjacent side, so we will call it as cis and transform. Next we are having this another type. This type is octahedral. Show geometrical isomers. These complexes contain symmetrical bidentate ligand. And what point should be noted, that these complexes contain symmetrical bidentate ligand. If I'll give the example, bidentate ligand, the example for bidentate is ethylenediamine, that is En. Ethylenediamine. Or I can say another example for bidentate is oxalate ion. The isomers for this complex this coordination sphere having the cationic charge, or I can say positive charge. How we can draw the two isomers? Here En is acting as a bidentate, so therefore it will form the structure in this way. Why is it so? If it is unidentate like chlorine, we will draw a single arrow key. For a bidentate or polydentate, we will need to learn this structure. We will learn this method to draw the polydentate, or I can say bidentate ligands. We will need to learn this structure. These structures are verified or approved by the iupac, and these structures are followed this one is transformed, this one is having the cis form, this one is having the cis form. The octahedral complexes of this type, another type we are having there is a single metal is having more than 2 or 3 ligands. This type of complex is having these 6 different ligands attached to metal atom and can have 15 geometrical isomers, which are not in our syllabus. This is all about the geometrical isomers. Also we can say the octahedral complexes with Ma3 B3 type. This one is another type. It may or may not be in your syllabus. Make sure to confirm. These types of octahedral complexes of this geometrical type also having geometrical isomers. This type of is also having the geometrical isomers where 3 ligand ends with donor atom are on same triangular face of the octahedron. If I'll draw the structure, you will understand what I'm going to say or what I'm saying to you. In these type of structures, when 3 ligand ends with donor atoms are on same triangular face of the octahedron, the geometrical isomer is known as facial or face isomers, in case the 3 ligand ends are on the same equatorial position. This one is triangular. I'm going to draw this one is we will call it as in this case the ligand ends are on the same equatorial position, 3 ligand ends are on the same equatorial plane of the octahedron around a meridian of the octahedron. This type of octahedron isomers are called meridional or isomers. There are numerous examples for face and isomers. Sorry for your inconvenience. We can draw the structure with the example of a mine with the multiple ligand ends. Another example we will have for this face and the meridional isomers. We can draw the complex this represents also face and the facial and the meridional isomer. This is whole about the facial and the meridional isomers. This is whole about the octahedral. Now you are able to, after few points to be remember. The complexes with coordination number 2 do not show geometrical isomers. So I repeat again, the coordination number with 2 and 4 do not show geometrical isomers. Next we are having the second point to be remember, that the complexes with coordination number 4 having tetrahedral geometry. Geometrical isomers is not shown by coordination number 4, but having tetrahedral geometry since all the positions are adjacent to each other. So it is now clear that the Y coordination number 4 complexes are not shown geometrical isomers because all the positions are adjacent to each other. This is whole about the geometrical isomerism.